So we'll discuss time-independent perturbation theory. So the point is that we have some system. Okay, so let us say we have a Hamiltonian. So let us say that, see, our aim is always to solve this equation, right? H, and I will write it as N is equal to En N. Okay, so H is the Hamiltonian. So our aim is always to solve this. Our aim is to solve this equation for a given Hamiltonian to get set of energy eigenvalues and set of energy eigenstates for all n. So this is the statement of the problem. Okay, so the connection between n and the wave function is known to us. Okay, or if you write down this n as a function of r, I mean, you project this into one of the coordinate, then you write this as some wave function psi n of r. Okay, so this is the connection between the ket and the wave function. So this we know. So we will work with this ket notation. It is somewhat simple to work with this ket notation. Now the problem is that most of the cases this equation cannot be solved. Okay, so in most cases this equation cannot be exactly solved. In fact, whatever cases in which it can be exactly solved, I think we have solved that already in the course. So this is important. In most cases, this equation cannot be exactly solved. So that means we cannot get, so this implies what? This implies we cannot get exact En or the ket n. We cannot get them exactly. Then we resort to something, some kind of an approximate technique. So perturbation theory is an approximate technique. Now here we assume that, so we assume that the Hamiltonian can be written as some h0 plus some lambda times h prime. Okay, we write it like that, such that this equation, that is h0, I will write this as n0 is equal to en0 n0 is exactly solvable. Exactly solvable, and h prime is much less than h0. That H prime is much, much less than H0. What does this mean? This means the energy content of H prime is much, much smaller than the energy content of H naught. When I wrote that magnitude, that means what I have in mind is the energy content of H prime is much smaller than. So if you are measuring this energy content in some electron volts, for example, H naught is 1 electron volt means H prime should be much smaller than 1 electron volt. Okay, however small it is good for us. So that is how, in that condition, perturbation theory works well. So if you look at this equation, this Hamiltonian form, so Hamiltonian H is written as H0 plus lambda times H prime. Please understand that this prime is not related to any derivative. It is a different term in the Hamiltonian. So we call this H naught as an unperturbed Hamiltonian because this can be exactly solved. So unperturbed Hamiltonian. And you call this H prime as perturbation Hamiltonian, or simply perturbation, or perturbed Hamiltonian. Okay. And what do we call this H? H we call as a total Hamiltonian. Okay. And this lambda, you call it as some small parameter. So what is the use of this small parameter? This lambda is usually it varies between 0 and 1. Okay. So if you imagine this is your lambda, so lambda equal to 0 corresponds to no perturbation, and lambda is equal to 1 corresponds to full perturbation. So lambda is some small value, means the perturbation is gradually been applied. So that's what it means. So this is a small parameter. Now, what is our situation? The situation is we can solve eigenstates and eigenvalues of unperturbed Hamiltonian, but we cannot solve eigenstates and eigenvalue of the total Hamiltonian. Okay, so uh, we can solve eigenvalues and eigenstates of H naught exactly. And they are, how did we denote them? En of 0 and get n of 0. So we call them like this. You can look at this equation. N0, En0, N0. Okay, and they are this. This is something which we can exactly solve. And we cannot solve We cannot solve this equation. That is Hn is equal to En n. We cannot solve this equation to obtain eigenvalues and eigenfunctions of the total Hamiltonian. That is En and set of ket n. So this is something which we cannot solve. Now, what perturbation theory does is it will try to get an approximate value of this En and n given the unperturbed eigenvalues and eigenstates. Okay, so perturbation theory gets approximate uh, values or approximate En and n, approximate En and n. Now, this approximation is something you can improve upon, and whether we have to improve or not is we are guided by the experiments in that case, because we try to uh, evaluate En and n up to some approximation and then compare with the experiments. If that's not matching, then we will try to do uh, a better approximation later. So that is how it has to be done. Now, there are two cases. The first one is we will try to look at the simplest case. So in this first thing that we will do is what is called non-degenerate perturbation theory. Okay, so this is called non-degenerate perturbation theory. Now, what do we mean by non-degenerate perturbation theory? Here we assume that the unperturbed energy eigenvalues what are they? They are denoted as En0 are all non-degenerate. There is no degeneracy. That is the assumption. So you may say that this is a very severe restriction, but first let us develop a theory for non-degenerate case. That means all are non-degenerate. That means for every eigenvalue there is only one eigenfunction. Okay. Now what do? We try to uh, write down. Okay, so let us express En and n. Remember, these are unknowns. En and n in a power series expansion. Power series expansion in terms of parameter lambda. What does that mean? That means I am going to write down my En as a zeroth order approximation. This will be unperturbed energy plus lambda times there is a first order correction En1 plus lambda square times there can be a second order correction En2 plus etc., etc., etc. This is an infinite series. Okay, so lambda is small and hence we expect that it will converge. Okay, but yeah, you will see that this issue of convergence is not very serious for us. And then we write this state n to a first order correction, it will be n0. This is the unperturbed state plus lambda times first order correction for the state n plus lambda square times second order correction n2 and so on. Okay, so this is basically a proposal. That means we are trying to say that this En can be unperturbed energy plus some correction, first order correction, second order correction, and so on. So what we will have to obtain is expressions for this. What we know, what we know is only unperturbed states and unperturbed energies. Okay, so that is what is known. The unperturbed eigenvalues are non-degenerate and they are known. En0 are known and n0 are known. That's all that we know because unperturbed problem can be exactly solved. Now let us substitute. So substitute this in this equation. H n is equal to En n. Okay. Now uh, we have to be a little bit careful in bookkeeping. Now let's say what is my H? H is nothing but H0 plus lambda times H prime. Okay. This operating on n. But what is n? N is nothing but n0 plus lambda times n1 plus lambda square times n2. This is an infinite series like this. This is equal to, on the right hand side, I have En. En is nothing but En0 plus lambda times En1 plus lambda square times En2 plus etc. This is an infinite series multiplied by another infinite series, namely n0 plus lambda times n1 plus lambda square times n2 plus etc. So this is the equation when I substitute this uh, expanded version of this En and n in the eigenvalue equation like this. Okay. So this is the equation from which we are going to derive everything. So this is uh, in some sense the most crucial equation. Now lambda is a parameter and in any equation we expect that the coefficient of every power of lambda should match between right hand side and left hand side. So for example, if you collect the coefficients of coefficients of lambda to the power 0. So suppose if I collect coefficient of lambda power 0, I will get some equation because I have to collect them in left hand side and right hand side, right? So H naught, so there is H naught here and N naught here. That is that does not have lambda. So left hand side I have H naught N0, and on the right hand side I have En0 and N0. So this is equal to En0 to n0. So this is the equation you will get if you collect the coefficients of lambda power 0. But this is something which we know. This is basically the statement of eigenvalue problem for the unperturbed Hamiltonian. Okay. So this is unperturbed problem, and which has been exactly solved. So we have nothing to do here. So coefficients of lambda power 0 has this kind of a equation, which turns out to be a statement of unperturbed problem. Now let us try to collect the coefficients of lambda to the power 1. Okay. And now you can see that h prime acting on n0 as a lambda, and h naught acting on n1 is also having a lambda on the left hand side, and right hand side en0 acting on n1 into n1, and en1 acting into n0. So there are two terms on the left hand side and two terms on the right hand side. Okay, so let us write them here. So that is uh, h0 acting on n1 plus h prime acting on n0. Okay, that is equal to en0 into n1 plus en1 into n0. So this is the coefficient of lambda 1. Okay. Now we can also collect the coefficients of lambda 2, lambda square. That's what I meant. So coefficients of lambda to the power 3, sorry, lambda square. Okay. So that will be, so h naught acting on n2 and h prime acting on n1. So there will be two terms here. Similarly, en0 into n2, en1 into n1. Correct? Will there be any other term? En2 into n0. There are three terms on the right hand side. You follow? So, okay. So maybe first let me. So left hand side is exactly like previous term. So let me keep this here. So I have h0 acting on n2 plus h prime acting on n1. Okay, there won't be any n0 because n0 has no lambda and there is no lambda square term here. So left hand side is only that much. But right hand side, you can have three terms. What are the three terms? So your en0 can be multiplied with n2 plus en1 can be multiplied with n1 and en2 can be multiplied with n0. So these are three terms that will be there on the left hand side, and we can keep on uh, writing it in this fashion. Okay, so for example, if you want to write a general and so on, if you want to write coefficient of lambda to the power r, okay, now I think from the pattern it is clear that you will have um, h naught acting on n of r plus h prime acting on n of r minus 1 on this side, and on the right hand side you will have sum over j is equal to 0 to r, okay, e n a into n of r minus a. Okay, so many terms will be there, r number of terms will be there. I mean, basically r plus 1 number of terms will be there on the right hand side. So this is a general coefficient of lambda power r. So from this equation we can write down coefficient of lambda power r in general. Whether it is required for us or not is not a question, but I'm just trying to state that one can write you can collect the coefficient of any lambda power r. Okay, so that is the expression that we will get. Now we are going to evaluate the corrections to energies and states in a progressive manner. Okay, we are going to evaluate them in a progressive manner. So now for that what we will do is we will uh, we will try to first use the coefficient of lambda power 1, because in that equation only I have first order correction for energy and first order correction for the state. Okay. So what do I do? So I'm going to now look at uh, so let us try to let us evaluate first order, namely En1 and N1. Okay, let's evaluate first order correction. So for that, so consider the coefficients of lambda to the power 1. We have already collected them earlier. That is this red equation. So let me write that down here. Um, Let me rewrite H0 acting on N1 plus H prime acting on N0 is equal to En1 acting on N0 plus En0 acting on N1. Correct? Now, so uh, first let us try to get En1. Okay, so okay, so let us get an expression for E. So for that, okay, so multiply multiply this equation with bra vector of n0 from left. In other words, you project this equation along n0. Then what happens? We have n0 h0 n1 plus n0 h prime n0 is equal to En1. See, En1 is basically a, a, a number. Okay, it's not an operator. So that means this will be n0 n0 okay, plus En0 to n0 n1. Is that clear? N0 n1. Now in the next step what we will do is, remember Hamiltonian H naught is a Hermitian operator. Okay, so since H naught is an Hermitian operator, the energy values are real. So that H naught can act on a ket that is to the right of it or also to the left of it, because left of it only its adjoint has to operate, but H naught is Hermitian, it is adjoint is same as itself, and hence, so note that since H naught dagger is same as H naught, H naught dagger is same as H naught, your N0 H naught is nothing but En0 N naught, because for a Hermitian operator, raw vector and ket vector will give same energy eigenvalue. If it is not Hermitian operator, this is going to be complex conjugate of this. But for Hermitian operator, energy eigenvalues are real. Correct? So since this is the case, we have, so what do I get here? So the above equation, so we get En0 N0 N1 plus N0 H prime N0 is equal to, now what is this N0 N0? Because we have unperturbed states which are orthonormal, so this will be equal to 1. So this is equal to 1. So right hand side I will have En1 and plus En0 N0 N1. Now what do you understand by this? This term and this term are same. This term and this term are same, and hence you can cancel. So this gives you that the energy correction, first order energy correction, is given by essentially the expectation value of the perturbed Hamiltonian with respect to unperturbed. So this is the first order correction in energy.
So here, the first thing which we should realize is that N0 and N1 are not orthogonal, right? We cannot directly tell that.
Exactly. I haven't assumed that whatever N0 and N1 are, you can say that they will go to 0 because the same term is there. Okay. So I haven't assumed anything about the properties of N1 here. Whatever it is, a similar term is there on both sides, so that will go to 0. Okay. So this is the expression for energy. Okay. So now you see that we have obtained an expression for the see, we know N0 and we know H prime, correct? So the first order correction for the energy is equal to the expectation value of the perturbed Hamiltonian with respect to unperturbed energy eigenstate. Okay. Now remember, since there is no degeneracy, there exists a unique eigenstate for En0, and that eigenstate I can use to find out the first order correction in the energy. Okay. So I think I am trying to do this slowly because there is uh, it's not difficult, but only a little bit of bookkeeping uh, is required. That's all. Okay. Now let us let us try to let's try to do our next thing. So let us try to now get, so in B. Okay. So we will look for expression for first order correction in the energy. First order correction in the state. So expression for first order correction in the state. Now let us go back to that
Excuse me, sir.
equation. Yes. Yeah. Go ahead.
Sir, in the previous question which we got, does it the previous question which we got, does it mean that the energy of first order is related to the energy of zeroth order?
It's not related to energy of the zeroth order. It is related to the expectation value of the perturbed Hamiltonian. Okay, so that is, let me write them in words. First order correction, first order correction in energy. That is what I called it as En1 is the expectation value of H prime in the state N0. Okay, so that is what that's what this means. Perturbation Hamiltonian is involved here. So what is the change in energy depends on H prime. Okay, so perturbation Hamiltonian is involved. Correct. This is the perturbation Hamiltonian. Okay. What was your question? Why should it depend on
I want to
unperturbed?
understand that is there any relation between first order and or is there any kind of relation between n plus one of order to n order?
Oh, so you are asking whether whether second order perturbation energy can be obtained from the first order states or correction states. Is that the question?
Yes, sir.
Yeah. So you will. That's what I said. You will only use these things progressively. So if you are getting a first order correction, then we will use that to get the second order correction and so on. Okay. So now let us try to
Okay.
ask a question. How do I obtain the expression for n naught? Okay, let us bring back this equation. That is, what is this equation? So let us go back to this equation. Okay, so let's say I'm becoming lazy to write. So let me just copy it here. So this is the equation that we had. The coefficient of lambda power 1. Now in this equation, let me now uh, pre-multiply this equation. So pre-multiply this equation with some m0, okay, where m is different from n, some other unperturbed state. Okay, so m is not same as n, some m0 I will multiply. Then what happens? I will have m0 h0 n1 plus m0 h prime n0, that is equal to en1 m0 n0 plus en0 m0 n1. Okay, so I have put this bra vector m0 everywhere. Now I can use the same logic that h0 is a Hermitian. So this one will be, so this h0 can act on this m0 to give an em0. So this is nothing but em0 into m0 n1. Okay, m0 n1 plus m0 h prime n0. And what will be the first term on the right hand side? Since m is not equal to m, n, this should be 0 because they are orthogonal. Those states are orthogonal. So that will be 0. So I have en0 into m0 n1. Okay. Now I can write this as, so let's say I bring this term on the right hand side. You see this m0 n1 is common to the term in the right hand side and the first term in the left hand side. So I can write down en0 minus em0 minus en0 m0 n1 is equal to m0 h prime n0. Or in other words, what I have is m0 n1 is equal to m0 h prime n0 divided by en0 minus em0. Now, if I claim that I have determined my state, do you understand? Okay.
Sir, just doubts. Here I have the doubt, sir. Here you have
Yeah.
told that N0 and M0 are orthogonal. But why not M0 and N1 are orthogonal, sir? Because you have claimed that M0 and N0 are orthogonal.
Yeah, that is correct. See, they are basically two states of a same orthogonal basis. I don't know what is N1 because I am going to, that is my job. No, I want to find out N1. So N1 is not a part of that basis, correct?
So
See,
you mean
all
that the zeroth order bases are all orthogonal, and first order states
correct.
are orthogonal.
That also I don't know. I have no idea about those states. No.
So, but you have
So
claimed
I
that
have
M0, that you have claimed that M0 and M0 are orthogonal because all zeroth order states are
that
orthogonal.
is
That's not your.
see the point is something like this. These states, that is N0, are eigenstates of H0. H0 is a Hermitian operator. Hermitian operator. Okay, such that H0 N0 is equal to En0 N0. Correct? And En0 are non-degenerate. Now you remember what all theorems that you have proved for Hermitian operators. Eigenstates corresponding to distinct eigenvalues are orthogonal. Correct? So I can say that this set N0 is a complete orthonormal basis. Is a complete orthonormal basis for the Hilbert space. Okay, it's a complete orthonormal basis for the Hilbert space. This much is understandable, right, from the postulates of quantum mechanics, because H0 is
Yes,
a
sir.
Hermitian operator. This is
Yes,
a
sir. Yes, sir.
complete orthonormal basis. What
Yes, sir.
does
Yes,
that
sir.
mean? That means you take any M0 and N0. This is delta Nm, correct? Delta Mn. I'm assuming normalization, so that is fine. So that is delta Mn. So you take any two vectors in this basis, they are orthogonal to each other, correct? So this is something that we are able to assume because of this. We can, I mean, we are assured this. This is something which we are assured. Now let's ask what is N1. So N1 is an arbitrary state. I don't know anything about it. It is an arbitrary state. Is an arbitrary state. I don't know what that state is. How do I know that this N1, since it is arbitrary, it is orthogonal to any M0? There is no way that I will know, right? So what I can say about this N1 is that I can say that this N1 can be expressed as, okay, so we can, because this is in the same Hilbert space for which this is a basis. So we can write this N1 ket as a linear combination of Cm into M0. This is something that I can write. This
And
is
you're only
something.
okay, sir. And you're projecting out only the M0 part, but whereas all other states are not. We
No,
cannot
now
say about.
see, this much is clear. This is agreed.
Yes,
This
sir.
is
Yes, sir.
something we can write down. Now, how do I find out Cm? What is Cm?
Take inner product with M0.
The inner product of
M0.
M0 with N1, correct? So what did I get here? This is Cm,
Yes.
correct? So whatever I have on the right hand side, again look at right hand side carefully. I have only unperturbed states M0, N0, En0, Em0. All these things are known to me. From these known things, I am now able to calculate the coefficient Cm of expansion of N1 in terms of again unperturbed states. Correct. So now what do I write? What do I write my the first order correction? Now the first order correction, the first order correction in state, okay, now can be written as N1 is equal to sum over M, okay, sum over M, M0 H prime N0, this is the matrix element of H prime between M and N, divided by En0 minus Em0 into M0. And of course, I must put a condition on this, that M is not equal to N. Okay, I must put a condition that M is not equal to N, because we want to see which other directions are contributing to the correction. The same direction, because if you say that N1 is proportional to N0, that means it is not adding anything as far as state is concerned. The state will change in the same. What I'm trying to say is that suppose if I have imagine I have a vector like this, and another vector in the same direction like this, another vector in the same direction like this. For all of them, unit vector is same. We are not going to get anything different with respect to unit vector. So all these normalized eigenvectors are like normalized vectors are like unit vectors. So we are not going to get any addition if we put in M0 in that. So we would like to know the change because of other states which are not along N0. And that is why this M not equal to N is important here. Okay. So this is the first order correction for the energy eigenstate. Okay. So
So,
okay, so maybe I can just pause and then ask if there are questions. Yes.
so one doubt. So you just said that m not equal to n. So what if we have considered the whole like the whole eigenstates of H naught as the basis? Then so there will be some vector n also, no, sir, that will form, like without that we can't form the whole complete basis. So, sir, how can we say that m not equal to n? Like we are taking out one vector from the basis, then how will it be complete?
Yeah. So what I'm trying to say is that see the point is something like this. We have no problem for completeness when you are taking completeness of the. So when you say complete, that means when you consider sum over n, this n0 and n0. Okay, when you take this and when you take sum over n, this is identity. So that is the completeness of this basis, correct? Yeah. So you are saying if you remove n0, then it will not be complete. Yes, that is correct. Okay, so that part is correct. Okay, so now what you can do is let's see. So let's say I write sum over m not equal to n, and m0 and m0, okay, plus, let's say I write n0, n0. Okay, so let's call this as identity. There is no problem, right?
Yes.
Okay, so now your sum over m not equal to n, m not equal to n, m0, m0 can be written as identity minus n0, n0, n0. Okay. Now let us say that we have. So now let us try to go back to this n1. Okay. So now your n1. Okay, n1 is like an identity acting on n1, right? So that is equal to sum over m not equal to n, m0, m0, n1, n1 plus n0, n0, n1. Correct? Is that clear?
Yes, sir.
So this is equal to sum over m not equal to n, cm into m0. That is what I have written there.
Yes.
Okay. Plus, I am making an assumption that I'm interested in choosing n1 or the correction only in the direction that is not along that direction. What does that mean? That means by my construction, I am making this 0. Okay. So because of that, in this summation, I don't have m is equal to n. So there is no problem for the completeness. Completeness is there, but so it is, so this n1 is chosen. N1 is chosen such that it has no overlap with n0. Why? Because if I don't choose that, okay, if I don't choose that, or if there is a overlap with n0, that overlap can be actually absorbed into n0 only. You are not getting any new information if there is an overlap with n0. So we want to get only the new direction information, and hence I will choose this such that it has no overlap with n0. What does that mean? That means your n1 is chosen such that it is orthogonal to n0. Corresponding n0 only. It's not orthogonal to another some m0, and that is what this CM is about. Correct? So it is orthogonal to corresponding n0.
Okay.
Sir, but why should only it be orthogonal, sir? The projection cannot be along any direction. So, for example, we told that there shouldn't be only no overlap, but that vector cannot be along any direction. No, no, why not? Why should you choose only to be orthogonal states in order to express it like that?
See, I am trying to see what is my
Okay, so
n0
I get it.
plus something I have to get. No.
Now I get it. The reason is that if you choose along any other arbitrary direction, it will still have some overlap on this n0. The
N0.
only direction, the only direction which does not have along n1 is the orthogonal state.
Correct.
Sir, but again with this, there is one last question which I want to ask. Whether this N1 and N1 are they orthogonal? For example, let me choose some basis. For example, in the last case, you have chosen that it is you have told that M0 and N1 are not. We cannot talk about those states. What about this N1 along N1 itself? Sir? It will be also orthogonal, right?
So
N on.
okay, so if I understand what you're asking is that suppose if I take M1 and N1,
Uh,
so
won't
you're
it be
asking
orthogonal?
what is this?
Yeah,
The
won't it be?
question that you're asking.
Yeah.
Okay, there is no reason to say that they have to be orthogonal because they are not as such eigenstates of any Hermitian operators. Correct? So I don't know really whether they are orthogonal or not. They need not be. Correct?
Yeah,
So
yeah.
they need not be orthogonal because
Then what about
they are not eigenstates of any Hermitian operator.
information operator?
Mm.
So but N2 also is orthogonal to N1 then. N3 also is orthogonal to N1 then. We are choosing it like that.
Yeah. So when we do this second order thing, then we will say that it should be orthogonal to N0 and N1. So that you have to get always some new information or new direction information.
Because if we choose it in the same direction, we can also get it by means of normalizing it. Yes. That can be factored out to normalizing.
Correct.
How is
Any other question? So I hope you have followed this because this is very. I mean, I feel it is not very difficult, but if there are questions, you please ask because this is basically the starting point of doing any business with quantum mechanics. So any real calculation you want to do, you should learn this perturbation theory.
So, and I think you also have chosen M0 and N1 as orthogonal, right? You
No,
told no? The previous derivations.
no, M0 and N1 I have never set to 0. M0 and N0 only I have set to 0 here.
Yes. M0 and N0. So will it be like, yeah. So similarly, will M1 and N1 will be orthogonal? So,
That's what I said here. I have no reason to believe they are orthogonal. That
okay,
was your
only,
earlier question, right?
yes. So in the first case, you are choosing M0 and N0 as orthogonal just because of the basis. I mean, the
Yeah.
direction you choose.
They are eigenstates of Hermitian operator, and hence they are orthogonal. Correct? These M1 and N1 are not eigenstates of any operator. They are just corrections. Okay. So is that clear? Okay. So now what we have done so far is that we have obtained an expression for first order correction in the energy and first order correction in the eigenstate. Okay. So very good. So now what we have to do, we have to go on and then ask what is the second order correction in energy, etc., etc., etc. Okay, maybe we will do that step. Let's look at second order correction in the energy. For that, what we have to take? We have to take the equation corresponding to this green coefficient of lambda square. Okay, so um, okay, so let us take that equation. Okay, so now let's say that let's call this as T. Okay, so the answer for this is not necessary. So now let's say second order correction. correction for energy. And that is what we called as En2. Now let us look at this expression. That is, I have H0 acting on N2 plus H1, H prime acting on N1. That is my left hand side. That's equal to En0 acting on N2 plus En1 acting on N1 plus En2 acting on N0. Okay. So now what we will do to obtain energy, what we have to do? We have to pre-multiply with um, N0. Okay. So that will give me, so N0 H0 N2 plus N0 H prime N1, that is equal to En0 N0 N2 plus En1 N0 N1 plus En2 N0 N0. Correct? Now you can see, let us do some simplification. N0 N1, we have chosen N1 such that this is equal to 0. There is no component from N1 along N0. So that is 0. And N0 N0 is 1. So this is 1. Okay. And what will this be equal to? Because this H can act on this, it will be En0 N0 N2. So this term will cancel with this term. Okay. So what we have, this implies we have En2 is equal to N0 H prime N1. So this was the question I think somebody asked earlier. The second order correction in energy depends on the first order correction in state. But since we already obtained this first order correction in state, I can write this N1 in the following fashion. So that is En2 can now be written as N0 H prime. Okay. And then what is this state? This state is nothing but sum over M not equal to N. Correct. M0 H prime N0 divided by En0 minus Em0 into M0. This is the state. Now remember this one is just a number or a constant. The state is only this M0. So that means this H prime is a linear operator, so I can write it as sum over, I can pull out the summation M not equal to N. So this constant, let me write out separately, M0 H prime N0 divided by En0 minus Em0. Okay, so these are just, this entire thing is a constant, and this N0 H prime and M0. This N0 H prime, so this factor N0 H prime will directly act on M0. Okay, that is how this is. Now you see this interesting thing. This is M0 H prime N0, and this is N0 H prime M0. What can we say about this? One should be the complex conjugate of the other, correct? So that means the second order correction in energy En2 is nothing but it is sum over m not equal to n m0 h prime n0 divided by this modulus square, because this is that complex number minus a complex number into its conjugate, En0 minus Em0. Okay, so this is the expression for the second order correction in energy. Okay, so we have obtained now the correction for the second order correction in the energy, right? Okay, so now we will try to just
So,
see some,
one
yeah,
doubt.
yeah.
So, H prime has to be Hermitian here
H prime has to be Hermitian, yes.
because it's not a very good, well-defined Hamiltonian. So, I was assuming it is not Hermitian.
No. H prime, see, let us say you have total Hamiltonian is equal to H0 plus H prime. Okay, so if H prime is not Hermitian, then the total Hamiltonian will also be not Hermitian, right?
Yes, yes.
So H prime has to be Hermitian.
Okay.
Yeah. Okay. So this is the second order correction. Okay. And we can go on asking what is the second order correction for the state and then obtain appropriate. You have to do a little more algebra, but along the same lines one can obtain. But let's not do that. Now let us say that we will be interested in just seeing how these formulas can be used. Okay. Remember, we are so we are still not what to say. We have still not used uh, any concept of degeneracy here. So far, we are talking all these expressions. Okay, so let me just list. So this is our main equation, and from here we collected the coefficients, and then this is the equation that talks about first order correction in the energy. Okay, so let us call this as equation 1. And then we went ahead and asked what is the first order correction for the state. So this is the first order correction for the state. Let's call this as equation 2. And then we talked about second order correction for the energy. So this is equation 3. Okay. So suppose if you are working in quantum mechanics, you write these three formulas in a chit and then keep that chit in your pocket, then you can do all problems. Okay, you can use perturbation theory to get all the problems. These are the three important formulas which we will use again and again in solving problems in perturbation theory. What I showed you today is how we are getting these formulas by expanding this state and energy in terms of some parameter lambda. So essentially what this means is the following. Suppose I have let's say these are energy levels. Okay, so let's say these are energy levels. So let's say this is E1, E2, Okay, E1 0, E2 0, etc. This is these are the eigenstates of H0, the unperturbed energy eigenvalues. Now let's say that you are applying a perturbation. Okay. Now what happens? These energy levels will also be, some energy levels will be there for the full perturbed problem. So let's say this is your H. Okay, so this is E1, this is E2, etc. Now what we are trying to say is that if you have some kind of a parameter lambda whose value is equal to 1 here and whose value is equal to 0 here, okay, each one of this energy level will gradually go to this level. This energy level will gradually go to this level. This level will gradually go to this level. So there is a continuous deformation of these energies such that the energy value will continuously go from E0, E1 0 to E1, E2 0 to E2, E3 0 to E0. This is what we are assuming what happens. And that is the reason why we are able to expand even in terms of in powers of lambda. Okay, so that is what actually what is called allows us to make an expansion, because this is the assumption that we are saying there is a continuous transformation of energy and the state from unperturbed set of energies to perturbed set of energies, unperturbed set of states to perturbed set of states. And this correspondence uh, is something which we can actually take it as granted because of non-degeneracy. Now, what happens if there is degeneracy? That is something which we would like to understand. Okay, so let me just present my next. Okay, so we will present the next theory, and then we will uh, do some examples in the next class. So the next theory is what we call as degenerate perturbation theory. Okay, we already know something about degeneracy. So let us say that uh, so here also we have a situation like this. We have H0, H Hamiltonian is equal to H0 plus some lambda times H prime. So this part is exactly like in the previous case. But what happens is that all the eigenvalues of H0 are not non-degenerate. Okay. So let us say let En0 be um, let En0 be some capital N fold degenerate.
So use G, sir, because I think small and capital. So G.
Huh? Should I write G?
Use yes, sir. G. Write G for generic because already we have small n.
Okay. So let's say G fold degenerate. Okay. What does that mean? That means there is a set which now I will call it as N0 comma K. Okay. So K is equal to 1, 2, etc. up to G are eigenstates of H0 with same eigenvalue En0. That is the meaning of degeneracy, correct? So there are G such states, all of them have the same eigenvalue En0. Okay. Now suppose if I use the same formula like in the previous case. Okay, so I want to find out uh, eigenvalues by just taking the expectation value of this situation. Now you see that that formula will not work. Okay. Why that formula will not work? Because you can see that every state, okay, so you know that every state in a g-dimensional space spanned by these vectors n0 comma k, spanned by these vectors, is also an eigenstate, of H0 with same eigenvalue. Same eigenvalue En0. Okay. Now you can see, so the situation is something like this. There is a degenerate subspace, correct? The set of set of the space of states that are spanned by this is a degenerate subspace. Okay, so let us call this as some Vg, which is equal to span of these vectors n0 comma k is a g-dimensional subspace of the Hilbert space. Okay, so this is what I am describing is of unperturbed problem. Okay, so now if I want to understand it in this language of this picture that I have drawn here, so the energy levels corresponding, there are so many energy levels, all of them have same energy. Okay, so this is the state n0 1 and this is the state n0 g. All of them have same energy En0. Correct. Now whatever states that we have obtained in this case are unperturbed states. Now let us say this is the situation for unperturbed Hamiltonian H0. Now here what happens, this En0 will become, so when I apply perturbation, what can happen is that these states may have different energies. Okay, so this can be En1, this can be En2, En3, En4, etc. This can be Eng. There can be different energies. So the energy for the full perturbed problem can be different. This is the energy of the full perturbed problem. Now Suppose if I know the, let's say that I know these energies, or I know these energy states. Suppose I know these states. Okay. Now if I imagine that I am trying to go back to this problem by setting lambda tending to 0, okay, will I get back to these states? Okay. So that is if we know, or if we knew. Of course we don't know. If you knew this n comma k, okay, uh, which are eigenstates eigenstates of h. Okay, so h n comma k can be written as e n k into n comma k. If you know these states, okay, if you knew this, will this states n comma k go to n0 comma k in the limit lambda tending to 0? So this is the question that we are asking. This question is we have said this will. So in this case, if you ask the same question, that is, I have n, so does it go to in the limit lambda tending to 0 to n0? If I ask that question, okay, the answer is yes. Answer is yes. They go to, n will go, if you tend lambda to 0 to n0. Now a similar question if I ask here, okay, so answer is that it's not guaranteed. Okay, so the answer is not guaranteed. Answer is in general no. Why no? And the uh, the the reason why it is no is because of the degeneracy. Now what happens if there is a degeneracy is that we do not know. See, if there is a degeneracy, we have obtained some g functions from solving h0 psi h0 n0 is equal to, but for the full Hamiltonian, whether those eigenfunctions are relevant or not, we have no idea, because not only those g functions, but there can be any g linearly independent functions can become a basis for the degenerate vector space. So so this is not guaranteed, but what is guaranteed is that this n comma k, as lambda tends to 0, will go to some set of g, uh, some set of g number of states, or some set of g number of states, okay, which can form a basis for this vector space Vg. This n0k also will form a basis, but it is not necessary that it will come to that basis. It will go to some basis. It is not necessary that it will come to this basis um, if you set lambda tends to 0. Now you can ask a question that what is the basis to which this will go? Okay. So what is the basis? to which this will go. And if we choose unperturbed states as that basis, then it is easy to do calculations like in the previous case. Okay. So, so now the question is how to choose that basis. How to choose that basis. Okay. Now it turns out that your so now H0 and H prime are two operators, right? So we know that N0K, N0K, K is equal to 1, 2, etc. up to G are basis, are eigenstates of eigenstates of what? H0 with eigenvalue En0. Okay, but so they span a VG dimensional, okay, and also form a basis for VG, the degenerate subspace of the Hilbert space. Okay. Now you can ask a question that suppose if we find, that is if we find, suppose if we find some, I do not know what symbol to use, let me say alpha 0 comma L as a state. Okay, maybe I can simply call it as N0. Okay, we can find, because it is still related to N, N0 comma let's call L tilde, just to say that these are some different states, as sum over K CKL into N0K. Okay, so in this case, where this L will go from 1 to G. So instead of these states, if you find some states like this, if we find states like this, okay, note that this N0 comma L tilde are also eigenstates of H0 with what eigenvalue? With eigenvalue
ENL.
En0, correct? En0, because it is some linear combination of states of Vg. That's all. This is another state of Vg. Okay, so note that this N0, these states are also eigenstates of with I0. Okay. Now, in addition, In addition, if they are also eigenstates of H prime, then the job is done. That means we must find, okay, so that means what? That implies we must work with common eigenstates of H0 and H prime. H0 and H prime in VG. That is the degenerate subspace. Okay. Does that mean H0 and H prime should commute? Does that mean the commutator of H0 comma H prime is 0? No, it is not required. Okay, the answer is no. Okay, so what it remains is that you must find. So how do you do that? You simply find diagonalize H prime. That means, so what should be done practically? So diagonalize, that implies diagonalize H prime matrix evaluated in this N0K basis. Okay, now if you diagonalize them, the eigenvalues of H prime are first order corrections for energy. First order corrections for energy. So you are going to have G eigenvalues, right? So note that H prime is a G by G matrix. Is a G by G matrix, and will have G eigenvalues. Okay, so as a result, what happens is ENL will be equal to EN0 plus ENL of 1. The first order correction will depend on L, correct? So that is how you get each of this one will be G eigenvalues, and each eigenvalue will be a correction. That is how the degeneracy gets lifted when there is a perturbation. And the eigenvectors of H prime matrix H prime matrix will uh, give what I have written here as N0 comma L tilde. L0 comma L tilde. Now you can use them. Okay, so once you so what are these n0 comma l tilde? These are the states to which this will come if lambda is tending to 0. Okay, so some set of g number of states I call them, right? They are not n0 of k, but they are. So in this case I can write that they are n0 comma l tilde. So where does it go? It will go to that common those states that are common eigenstates of both h0 and h prime. Okay, so that is so once you find this, then we can use a similar similar uh, exercise like in the previous case. Then find first order correction. Okay, first order correction appealing to a similar formalism as in previous case. Okay, so this is the issue with respect to the second order, the first degenerate case. Okay, so let us try to just take a simplest illustrative example. We will work out more examples in the next class, but let's just a simple illustrative example. So let us say that I have a Hamiltonian, which is, so let us say that I have an energy E that is doubly degenerate. Okay, that means I have E0 and 0E as the Hamiltonian H0 in the degenerate subspace. That means we have a degenerate subspace is two-dimensional. So all operators in two-dimensional will be 2x2 matrices. So this is my H0. Now let us say we will have our H prime, which can be written like this. Let us say 0 and some potential. So let us call that as V and V star and 0. It can be complex number. This will be Hermitian, right? 0 V, V star 0. I'm taking simple Hamiltonian. Now there are two eigenvectors corresponding to this one. That is, I have 1 0 and 0 1. Okay, these are the two eigenvectors corresponding to H0. So you know that H0 acting on this one will be E into 1 0. So the eigenvalue equation is satisfied. Now suppose you want to calculate first order correction. So use the non-degenerate formula. So your first order correction, so let us call that corrected one as E tilde, will be E plus, so you are going to write 1 0 0 V V star 0. Okay, let us also forget about this star. Let's say that it is real. So 0 V V 0 and then 1 0. So what will this give you? This will be this is nothing but plus 1 0 into 0 V. Okay. Okay, so that is equal to 0. So that means this is equal to E only. So there is no change in the energy. Same thing you could have done with 0, 1, you will get the same thing. That means the energy is not changing. If I forcefully use the same non-degenerate formula, okay, so this is what it is. But now you realize that your H prime is a V times 0, 1, 1, 0. Okay, and notice that this 1, 0 and 0, 1 are eigenvectors of H0, but not eigenvectors of H prime. They are eigenvectors of H0, but not eigenvectors of H prime. Okay, so now what we should do, we should find out the common eigenvectors of H0 and H prime. Since energy is same, both the eigenvalues are degenerate. Okay, so uh, so you know that any vector which is a linear combination of 1, 0 and 0, 1 is also an eigenvector. Suppose if I take some xy with a 1 by square root of x square plus y square, okay, so is an eigenvector of H0 with eigenvalue E. You can verify that with eigenvalue E. Now we have to ask a question: what should be the values of x and y such that it is also an eigenvector of H prime? Okay, so we ask a question: what should be the value of x and y such that it's also an eigenvector of H prime? So now if you ask that question, you will see that if you take 1 by square root of 2 into 1 comma 1, okay, so is an eigenvector of H prime with eigenvalue plus V. Similarly, you can say 1 by root 2 1 minus 1 is an eigenvector of H prime with eigenvalue minus V. Okay, so if you choose these two eigenvectors, then you get eigenvalue plus V and minus V. So now what happens for the full Hamiltonian? Now what is our H? H is nothing but E, V, V, E. E, V. This problem can be exactly solved because, as I told you, eigenvalues will be corrections in the energy. So from perturbation theory, we have E plus V and E minus V are the energies, new energies. That is, E1 tilde is E plus V and E2 tilde is E minus V. Unperturbed case, E1 0 and E2 0 are same as E. So now we have two different energies, correct? But we could have also written this matrix directly, correct? Could have also written this matrix directly and find out eigenvalues. So eigenvalues will be E minus lambda the whole square minus V square. That is equal to 0. So that will be E minus lambda plus V into E minus lambda minus V is equal to 0. That implies lambda is equal to E plus V and lambda is equal to E minus V. So this is exactly solved. I'm exactly finding the eigenvalues of this equation, and this is what I have got as a perturbation. So with the first order perturbation itself, I have got the exact eigenvalues here. Okay, this is the simplest example that I have taken. where the first order correction is giving us the exact result. Okay, but in general you will get only some approximate result with the first order correction. Okay, so yeah, so today more or less I only spent time on formalism, but we will take up some examples and kind of some problems in the next class. So I will stop here. If you have some questions, you can ask.